Okay, this is day 5 in chapter 1, and in this lesson we're going to take a look at two different things. First of all, we're going to look at a graphical test for even, odd, or neither. So this will be an alternate way instead of plugging a negative x in everywhere for x. And we're also going to introduce the idea of conics, which is a kind of relationship that oftentimes is not a function. But first of all, we're going to start with the graphical test for even, odd, or neither. So one way to test for this that we learned yesterday was that you could plug a negative x in everywhere and take a look at what happens with your signs. If they all change, it's odd. If none of them change, it's even. If some change and some don't, it's neither. But this is going to be a different way of looking for that same thing. And this is going to be based on different kinds of symmetry that a figure may exhibit. So symmetry is when a shape matches itself when you do a certain kind of transformation. So it turns out that all even functions are symmetric over the y-axis. So in other words, if you can fold your picture over the y-axis and the left and the right-hand sides match, then that's an example of an even function. So let's take an example, f of x equals x squared minus 3. So that is a parabola that's been moved down 3 units. So some of the points that would be on this graph would be 0, negative 3, 1, negative 2, 2, 1. And on the left-hand side, you're going to have negative 1, negative 2, and negative 2, comma 1. So here's your parabola. And as you can see, this parabola is symmetric over the y-axis. So that means it's an even function. We have symmetry over the y-axis. So if you can picture folding your graph over the y-axis, the left and the right-hand sides match. Now, just to come back and prove this with the algebraic technique, in the algebraic technique, you'd evaluate f of negative x, which would put a negative on the x inside of being squared. That would produce x squared minus 3. And because everything stayed the same as it was originally, we know that that's an even function. So this is the algebra test. But if you have a graph, or if you can quickly make a graph of a shape, sometimes it might be easier to figure out if it's even, odd, or neither from that. So odd functions, all odd functions are symmetric over the origin. So symmetry over the origin is also called point symmetry. And the way to test for that is you want to check to see if the graph looks the same upside down as it does right side up. So an example of this would be the cubic f of x equals x cubed minus 4x. If you want to go ahead and use your graphing calculator to make this, this is a cubic that crosses the x-axis in 3 spots, negative 2, 0, and positive 2. And the graph of it kind of looks like this. So this is f of x. And if you were to take your paper and completely rotate it around, (180 degrees), well, that didn't work. If you were to take your paper and completely flip it upside down, this graph looks identical when upside down as it does right side up. Now, again, you can double check that work by doing the algebraic test for this. So if we imagine plugging a negative x in every place there was an x, we're going to notice that you end up with negative x cubed plus 4x, which means that all the signs changed. And that is an example of an odd function. So odd function is symmetric over the origin. Even function is symmetric over the y-axis. And if you have a function that doesn't exhibit either one of these kinds of symmetries, if it's not able to be folded over the y-axis or it doesn't look the same upside down, then it's a neither. Okay. The next topic that we're going to take a look at is recognizing conic sections. So conic sections are formed from taking slices through something called a double napped cone. So a double napped cone is when you have two cones that are identical in size, facing each other, and their tips, the very point of the cones, touch each other. Depending on which way you slice through this double napped cone, you can create different kinds of shapes. So this is the intersection with the edge of the double napped cone and your plane. So if you slice through on an angle, you can kind of get a parabola being formed right here. If you slice through horizontally, you would get a circle being formed right there. If you slice through on not as drastic as an angle as the one before, you can get an ellipse. And if you slice through vertically, you can get something called a hyperbola. These are the four different kinds of relationships that can be created by slicing planes through a double napped cone. But when we're doing this, we have to be able to recognize what kind of shape we're dealing with just from their equations. So the first kind of equation that we want to talk about is just the normal parabola. A normal parabola has an equation of y equals, and you have to have x squareds. You can have regular x's and regular constants. An example of this might be, for example, y equals 2x squared minus 4x minus 3. And this, if you think about what a parabola looks like when you draw it on your x and y set of axes, you might see something like this. And this does pass the vertical line test. So that means this one's a function. And when you go to graph it, since the equation is already solved for y, you just graph it as it is. You type it right into your graphing calculator, y equals, and then you type in the 2x squared minus 4x minus 3. However, there are many of these shapes that can be created from the intersections of planes and double napped cones that are not functions. And so we want to spend a little bit of time and talk about some of those. The first one I want to address is a sideways parabola. A sideways parabola is going to have x to the first power and y's that are squared, y's to the second power. This is the key indicating feature of a sideways parabola. An example of that might be something like x equals 3y squared plus 5. Now, these would be examples of equations that you haven't seen before because these are not going to be functions. If you did want to graph this equation, you would have to get the equation solved for y. So the first thing you would do is subtract 5 from both sides. Then you would divide both sides by 3. And then you would take the square root of both sides. Now remember, when you're taking the square root of an equation, you would have to have a plus and a minus. So this would be y equals plus and minus the square root of x minus 5, all getting divided by 3. So if I actually wanted to graph this on my graphing calculator, I'd have to graph the top and the bottom equations separately. So there'd be positive square root of x minus 5 divided by 3, and then a second equation, negative the square root of x minus 5 divided by 3. Just to show you a quick drawing of what this looks like, this is the top half, and this is the bottom half. So basically what you have is a parabola that's traveling sideways, and of course that does not pass the vertical line test, therefore sideways parabolas are not functions. The next group of formulas, I'm going to lump them together, circles, ellipses, and hyperbolas. One of the main defining features about all three of these is that both the x's and the y's are squared. So if you see an equation in which you have both x's being squared and y's being squared, then you must be one of these three things, either a circle, ellipse, or a hyperbola. So let's take a look at each and talk about them. For circles, The numbers, so this is how you're going to tell the difference between circles, ellipses, and hyperbolas. The numbers in front, we call those the coefficients, must be the same number and the same sign. Now, when I tell you the same number and the same sign, I'm talking about once they're both on the same side of the equation. So make sure that you bring all of your x squareds and all of your y squareds to the same side, and then make the determination as to what type of an equation it is. So same number and same sign when they're residing on the same side of the equation. So an example of something like this might be 3x squared plus 3y squared equals 48. If you divided both sides of the equation by 3, you'd have x squared plus y squared equals 16, which of course we know is the equation of a circle with a radius of 4 centered at the origin. So if I were going to draw this, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, it looks something like that. But if you wanted to use your graphing calculator to draw this, you would have to get the equation solved for y. So first we'd have to move the x squareds over to the other side, and then we'd have to take the square root of both sides. Again, remember, when you're taking the square root, you're going to get a plus and a minus. So the equations, there's actually two of them here that you'd have to graph, are positive the square root of 16 minus x squared, and the negative square root of 16 minus x squared. So the positive one would give you the top half of the circle, and the negative one would give you the underside of the circle. Okay, next let's talk about ellipses. So for ellipses, when you bring the x squareds and the y squareds to the same side of the equation, what you're going to get for the coefficients are going to be different numbers, but they need to have the same sign. So either they're both positive or they're both negative. So an example of something like that might be 3x squared plus 6y squared equals 48. So again, to be able to graph this on your graphing calculator, you'd have to get the equation solved for y. That would involve moving the 3x squared over to the other side. So you'd have 48 minus 3x squared. Then you'd want to divide both sides of the equation by 6. So y squared equals 8 minus 1/2 x squared. And then you would take the square root of both sides. So y squared equals, y equals plus or minus the square root of 8 minus 1/2 x squared. Now ellipses have one of two different ways of looking. They have what's called a major axis and a minor axis. And sometimes when you draw ellipses, they're longer in the x direction than they are in the y direction. In this case, we would say the major axis is the x-axis and the minor axis is the y-axis. But sometimes ellipses are longer in the y direction and can look like this. So in this case, we would say the major axis is the y-axis and the minor axis is the x-axis. So depending on what this formula is and what the coefficients were in front of x's and y's, you can get one of those two looks. And again, this is not going to be a function because it won't pass the vertical line test. The last type of formula is a hyperbola. And again, once you get the x squareds and the y squareds to be on the same side, here's what you're going to notice about the coefficients. The coefficients must have different signs. So one of them has to be positive and the other one has to be negative. They might even be the same number. But if they're different signs, when you get them on the same side of the equation, then that's a hyperbola. So an example of that might be something like 3x squared minus 6y squared equals 48. So in this case, I have different numbers and different signs. But even if that 6 was a 3, if they're different signs, it's a hyperbola. Again, in order to solve this, you'd have to get the y by itself. So we'd have to move the 3x squared over to the other side. So that would be y squared equals 48 negative 6y squared equals 48 minus 3x squared. Then you'd want to divide everybody by negative 6. So that would be negative 8 plus 1/2 x squared. And then you would want to take the square root of both sides. So that would be y equals plus or minus the square root of negative 8 plus 1/2 x squared. And again, hyperbolas can look one of two ways. They can be what's called an up and down hyperbola, which would look like this, or they could be a left and right hyperbola, which would look something like this. In either case, you're not going to pass the vertical line test. And the best way that I can describe what you're looking at when you see the graph of a hyperbola, it kind of looks like the stitching on a baseball or the seams on a basketball. But in either way, it will not pass the vertical line test. And again, for all of these ones that are not functions, you actually are graphing two separate equations. One gives you the top half and one gives you the bottom half. Okay, you are now ready to try the homework for tonight.